brittle fracture of normally ductile materials. For example, the example we saw at the beginning of the last lecture, the brittle fracture of the oil tanker around the girth. It has demonstrated the need for a better understanding of the mechanisms of fracture. So fracture mechanics is the study of the material's ability to withstand stress in the presence of a flaw. So this subject allows quantification of the relationships among material properties, stress level, the presence of crack-producing flaws, and crack propagation mechanisms. We will also use another term, which is the fracture toughness. Fracture toughness is the resistance of a material to failure in the presence of a flaw. And the stress applied to the material is intensified or amplified by the flaw. After comparing the ideal materials to real materials, we find that the measured fracture strengths for most materials are significantly lower than those predicted by theoretical calculation based on atomic bonding energies. So here we have the stress-strain curve for a perfect material with no flaws. And this stress and strain, especially for the tensile strength, is calculated based on atomic bonding energy. Versus the real material, and this is a carefully produced glass fiber, which has a tensile strength that is lower than the ideal material. And also it's quite brittle because it doesn't have the plastic deformation. And next is typical ceramic. Again, it's a brittle material, but the tensile strength is much lower than the perfect material. And next, we have typical strengthened metal. It's quite ductile, but again, the mirrored tensile strength is much lower than the perfect material. And lastly, we have typical polymers. It's even lower. So therefore, we say the tensile strength of the mirrored engineering materials are much lower than the tensile strength of perfect or ideal materials based on the calculation of atomic bonding energies. And the reason can be explained by the presence of microscopic flaws or cracks that always exist under normal conditions at surface and within the interior of a body of the material. Flaws and micro voids at the surface of the material or within the material are stress concentrators or amplifiers. So if the applied stress is sigma 0 on the piece of metal, at the tip of the crack, this value is much larger than the applied stress. So the relation between the stress at the crack tip here and the applied stress is described in this given equation, where sigma m is actually the maximum mass wall, the maximum stress within the material at the tip of this crack, equals to 2 times sigma 0, which is the applied stress, times square root of A over rho T. So let's explain the terms in this equation. Rho T is the radius of curvature of the tip or of the crack at the tip. And sigma 0 is the applied stress to the entire material. And sigma m is the stress at the crack tip, which is the maximum value. And A, if the crack is at the surface, then A length is the length of the surface crack. But if the crack is within the material, is an internal crack, then we need to divide the length of the crack by 2 and then use in this equation. So we can say that half A is the half length of an internal crack. And sometimes we combine this coefficient 2 times square root of A over rho T, and we call it as the stress concentration factor K sub T. The stress concentration factor K sub T, if we rearrange the previous equation, we can see this K sub T actually is the ratio between the sigma m and sigma 0, where the sigma m is the maximum stress at the crack tip, and sigma 0 is the nominal applied stress sigma 0. So if you take a look at this stress profile, we can see that the magnitude of this stress decreases with distance away from the crack tip, or the stress at the crack tip is a maximum value. It's much larger than the applied tensile stress sigma 0. Or we can calculate KT, the stress concentration factor, with the length of the crack and the curvature at the crack tip, or the radius of the crack tip. So the stress concentration factor KT measures the degree to which an external stress is amplified at the tip of the crack. Using fracture mechanics principles, an expression has been developed that relates the critical stress for crack propagation and crack length A. So this critical stress for crack propagation is the stress for the crack to grow. So when the applied stress is above this critical stress, then the crack starts to propagate or start to grow. But if the stress is below this critical stress, well, then the crack will not grow. So that's the critical stress for crack propagation. And crack length is A. And now here we say the fracture toughness is K sub C. Didn't we just use a very similar term or symbol for another term, which is the K sub T? Okay, so don't get confused by the two terms. They are very similar, but they are different. Fracture toughness, K sub C, and K sub T is the stress concentration factor. And this factor is a dimensionless number because it's the ratio between two stresses. Now, this relation is Kc, the fracture toughness, equals to Y times sigma C, which is the critical stress for crack propagation, times square root of pi A, where Kc is the fracture toughness, a property that is a measure of a material's resistance to brittle fracture when a crack is present. And it has an NURO unit, which is the unit of this stress, megapascal, times the unit of square root of A, which is the square root of length, square root of meter, or PSI, pound-force per square inch, times square root of inch. And sigma is the applied stress, or sigma sub C actually here is the critical stress for crack propagation, and A is the flaw size. Same idea, if it's an internal flaw, then we need to divide the entire length by 2. That will be the A value. But if it's a surface flaw, then it's just A. The length is just A. And Y is a geometry factor. And if we have an internal flaw, then Y equals to 1.0. But if it's a surface flaw, we use 1.1 for Y. For the crack surface displacement, there are 3 different modes, which are shown in those figures. The first mode is called opening or tensile mode. And second, mode 2 is the sliding mode. Mode 3 is tearing mode. But in this class, we will only focus on mode 1, fracture toughness, which is the plane stress fracture toughness. And to calculate for the plane stress fracture toughness is a very similar expression as before, but we just add a Roman letter 1, or looks like I here, in the subscript to indicate this is the plane stress fracture toughness, equals to y, which is the geometry factor, and sigma here, which is the applied stress. So instead of the critical stress for crack propagation, and sigma here used for plane stress fracture toughness is the applied stress. Square root of pi times a, which is the internal length, which is the surface crack length, or half of the internal crack length. So KIC, the plane stress fracture toughness, is cited for most situations and is a fundamental material property that depends on many factors, and the most influential factors are the temperature, strain rate, and microstructure. But since it's a material property, and in most of the calculations, this KIC, the fracture toughness, will be given, or you need to look for it based on other given informations. So in summary, the plane strain fracture toughness, KIC, is a material property. It is the resistance of material to brittle fracture in the presence of a crack or of a flaw. And this is the equation. And in this equation, KIC is the plane strain fracture toughness. And sigma is the applied or imposed stress. And A is the flaw size. F or Y is the geometry factor. And we use 1.0 for internal flaw, or 1.1 or 1.12 for surface flaw. So be very careful with the A values and the geometric factor. Sometimes you can see this factor is expressed in F, or sometimes we use Y. So they're all the geometry factors in the calculation of the plane strain fracture toughness. So A, this is the flaw at the edge or on the surface, and if it's a surface flaw, then we use the length of this flaw, A, in the calculation. But if it's an internal flaw, then 2A is the entire length. Therefore, in the equation, we need to divide the entire length by 2 to get the A value in the calculation. And for the geometry factor, the surface flaw has a geometry factor of 1.12, and the internal flaw has a geometry factor of 1.0. So when we design against the fracture growth, 3 variables must be considered for design. The first one is the plane strain fracture toughness, which is the material property. So if we have chosen the material to be used in certain application, this plane strain fracture toughness is determined. And the second variable is the applied or imposed stress. So when we design the structure again, we may already know what kind of load or what's the value of the applied stress on the component. And A is the flaw size. So with 2 given variables, we can solve a third one. So that will give us different types of design projects. So the first type will be if we know the material by knowing the plane strain fracture toughness, or we know the plane strain fracture toughness by knowing the material, and also we can measure the internal flaw size or the flaw size at the surface. So when we know those 2 values, we can find the maximum allowable stress, applied stress on the component. So the stress must be no bigger than this value. Again, this is rearrange the equation from the plane strain fracture toughness equation. The second design we can do is if we know the material, so we know the plane strain fracture toughness, and we know the applied stress, then we can calculate for the maximum allowable flaw size. So again, this is the maximum allowable flaw size. As long as the flaws are smaller than this one calculated from the given equation here, then the material is safe to be used in the component or in the structure. So keep in mind that flaws or micro cracks are always present in the material. There is no perfect material. Example 1. A large steel plate used in a nuclear reactor has a plane strain fracture toughness of 80,000 psi square root inch, and it's exposed to a stress of 45,000 psi during service. What is the maximum allowable size of crack at the edge, which means at the surface of the plate, before the crack is likely to grow at a catastrophic rate? And assume the geometry factor F equals to 1.12. Again, sometimes in some resources you will see this letter F. In some books, for example, in the textbook, it uses this letter Y for the geometry factor. But you know, right? Or we know they are the same. Okay, clearly this is a problem involves plane strain fracture toughness, which is the KIC, and the applied stress is given here, and we're looking for the size, right? The maximum allowable size, which is the critical size for the crack at the edge. Well, clearly we're going to use the equation which is converted or transformed from the plane strain fracture toughness equation, where AC is expressed in terms of the plane strain fracture toughness and the applied stress as well as the geometry factor. So again, all of the values are given, and we just need to use the applied values to calculate for the critical size or the maximum allowable size of the crack. Or you can start from the plane strain fracture toughness equation and substitute the values and then solve for A. And A is 0.8 inch, which means this is the maximum allowable size of the crack at the surface of the plate. As long as the cracks are smaller than this maximum size, then it is safe to be used. Design example 2, aircraft wing. An aircraft component is made from a material has a plane strain fracture toughness 26 megapascal square root meter. It has been determined that fracture results at a stress of 112 megapascal when the maximum internal crack length is 9.0 millimeter. And for the same component and alloy, compute the stress level at which fracture will occur for a critical internal crack length of 4.0 millimeter. So let's write down the given information and to see how should we solve this problem. So first we are given with the fracture toughness is given and the applied stress is given. Since we're looking for another applied stress level, so let's call this is the situation 1, right? So case 1, sigma 1, when the applied stress is 112 megapascal and the maximum internal crack length, the AC, is 9.0 millimeter. And now for the same component and alloy, so case 2, we have the same, everything is the same except for we know the crack size now is AC, so this is AC1, and that is AC2, it's 4.0 millimeter, and we are looking for the stress level, which is sigma 2 equals what? Well, again, we will start from this plane strain fracture toughness equation, which equals to y sigma applied stress times square root of pi a. Well, clearly, if we need to find the sigma 2 value, we know the fracture toughness case IC, and we know the critical internal fracture length A, and we just need to know this sigma value. And pi, of course, is a constant. Therefore, we only need to know the geometry factor y first. And y can be calculated from case 1. Since we know, same thing, the fracture toughness KIC is the material property, which is the same value, equals to y, which is also the same value because it has the same component in alloy. That means this constant, geometry constant, is also the same. Y times sigma 1 given times pi over, or square root of pi times 2 times pi times AC1, and the critical internal crack length A1 is also given, and now the only one that is not known is the y. So that will be our first step. Get the y value from case 1, and second step is with the calculate y value, we calculate for the applied stress level at the second situation when the crack length is 4.0 millimeter. So let's write down the solutions. Given that a fracture occurs for same component using same alloy, the parameter y will be the same for both situations. Solving y for the conditions and which fracture occurs or occurred using this equation, and the A value is 9.0, and don't forget to convert the length from millimeter to meter. And the sigma C, the critical stress, is 112, and this fracture toughness is 26, and y is solved to be 1.38. And next, we're going to solve for the critical stress level for the given crack size, which is 4.0 millimeter. And this critical stress level is calculated to be 168 megapascal. Again, don't forget to convert the units, especially for the length of the crack. It's a very small value, therefore the unit is not in meter, it's in millimeter, but you need to convert it to meter for your sigma or y to have the correct unit. So the fracture mechanics are very important. First, it can help us to choose the right material. And if we know the maximum size A of flaws in the material and the magnitude of applied stress, we can select materials with enough fracture toughness to prevent flaw growth. And second, it can help us to design the component. Then if we know the maximum flaw size of the material, which is the A value, we can design the component such that the maximum stress on the component never exceeds the fracture toughness. It can also help us to design the processing method. If we know the component design and apply the stress sigma, we can develop a manufacturing method such that the maximum flaw size will be below the critical size.